In this video, we're going to talk about elimination. Specifically, the elimination reaction we are going to talk about is the E2 elimination reaction. The E2 reaction is the biomolecular elimination reaction. Biomolecular means two molecules. So you can see that in this reaction we have a base and an acid. The elimination part of the reaction implies that we are forming a double bond. In the case of the E2 reaction, we are forming a carbon-carbon double bond. Our base, shown here, has to be a strong base. And I'm going to draw the electrons that are shown there for the generic base in blue. They're going to come and pull off a hydrogen, and that is going to form the base hydrogen bond. So this blue lone pair becomes the base hydrogen bond. When that happens, the carbon hydrogen electrons come down to form a pi bond. So the carbon hydrogen electrons come down to form a pi bond. Then the carbon L bond, and L is supposed to be the leaving group, comes down to form a lone pair on the leaving group. The carbon leaving group bond forms a lone pair on the leaving group. Notice that in this reaction we are going from our electron-rich base to the electron-poor substrate. The carbon is going to be electron-poor and have a delta plus because the leaving group is going to be an electronegative atom that is pulling away electron density. So the delta minus would be on the leaving group. Let's look at a specific example of an E2 reaction. In this case, our Lewis base is hydroxide. Let's follow the electrons. The lone pair on the hydroxide comes down to form an oxygen-hydrogen bond. And it's not shown over here, so I'll draw out that bond. So this blue lone pair becomes the oxygen-hydrogen bond in the water here. The carbon-hydrogen bond comes down to form a pi bond. The carbon-hydrogen bond comes down to form a pi bond. And in this case, our leaving group is Br minus. So the carbon-bromine bond is going to break and form a green lone pair on bromine. And I'm going to draw in the other electrons here so we can keep track of what's happening. So the carbon-bromine bond becomes the green lone pair on the Br once it falls off. So this is the green lone pair on the Br minus. Notice that we are using a strong base. We are pulling off a nearby hydrogen and forming a new pi bond. Let's look at this animation so we can see what this looks like visually. So here's the reaction that we're going to look at. First, let's start in by zooming in on the reaction to make sure we understand what's going on. I'm going to add in a couple of lone pairs here on our base and on the bromine so we can follow what's going on. Okay, so let's follow the arrow here. The blue lone pair from T-butoxide. And T-butoxide, let me draw out just so you know what that looks like. T-butoxide is going to look like that. And I drew it out with a blue lone pair. So T-butoxide comes down and picks up that hydrogen there. That means that what it looks like after the reaction happens is like that. The hydrogen-carbon bond comes down to form the pi bond. So the carbon-hydrogen bond comes down to form the red pi bond over here. And finally, the leaving group falls off. Those green electrons forming that carbon-bromine bond become a lone pair on the bromine. I'm going to draw the bromine out over here too so you can see what it looks like. So the carbon-bromine bond become that green lone pair on the bromine. This particular reaction is actually showing a second elimination reaction. And you can see that here where a second equivalent of t-butoxide is forming an oxygen-hydrogen bond. A second pi bond is being formed where the carbon-hydrogen bond breaks. And a second bromine is falling off. Now that we've gone over the reaction mechanism, let's look at the animation. In the first step, you can see the t-butoxide over here. It's going to pick up a hydrogen on our cyclohexane. Here comes in t-butoxide, pulling off a hydrogen and forming the double bond. Let's look at that one more time. T-butoxide comes in, pulls off a hydrogen, forms the double bond, and Br- comes off. Now let's look at the other one. T-butoxide comes in, pulls off the hydrogen, forms the double bond, and kicks off the other Br-. Now let's compare substitution to elimination so we can learn how to tell the differences between these types of reactions. In our substitution reactions, we have a nucleophile come in, kick out the leaving group, and replace it. The nucleophile becomes connected to the substrate. In the elimination reaction, the base comes in, and instead of replacing the leaving group, it pulls off a hydrogen. This results in a carbon-carbon double bond. You'll notice that one of the key differences here is in the elimination reaction, we have to have that hydrogen that I have colored in green there. We call that the beta hydrogen, and it must be present for elimination to occur. If you're counting, this would be the alpha carbon with the alpha hydrogens, and this would be the beta hydrogen with the beta carbons. If we don't have that hydrogen there, the elimination reaction can't happen. So the key difference with this reaction is you have to have the beta hydrogen, and you're forming the carbon-carbon double bond as your product. Let's look at another example of an E2 reaction. Again, we have a strong base, and in our substrate, we're going to have a leaving group, and we are forming a new carbon-carbon double bond. Let's follow the electrons. The blue lone pair on the base becomes an oxygen-hydrogen bond. Blue lone pair becomes oxygen-hydrogen bond. The carbon-hydrogen bond becomes the new pi bond. The carbon-nitrogen bond becomes a lone pair on the nitrogen. Carbon-nitrogen bond becomes a lone pair on the nitrogen. Here's another example. In this case, we're forming a new triple bond. So our E2 reaction is forming an extra pi bond. Let's follow the electrons. The lone pair on NH2- becomes a nitrogen-hydrogen bond. The carbon-hydrogen bond comes down to form a pi bond. And the carbon-bromine bond comes off to become a lone pair on the bromine, forming Br-.